This video examines the question of measuring variability in our sample and reviews different measures based on a descriptive statistical approach. That is, when we're strictly describing our sample and not seeking to make inferences about the larger population. Previously, we've talked about measures of central tendency like the mean, median, and mode. And while measures of central tendency are probably the most obvious descriptive statistics, to truly understand data, simply knowing the mean score or central tendency is not enough. Let's say I tell you that my pet weighs 2 kilograms more than the mean for its species. Is this no big deal, or should I be contacting the Guinness Book of World Records? Well, it depends on the variability that exists within the data. If my pet is a rhinoceros, 2 kilograms above the mean is nothing. Many rhinos are hundreds of kilograms above the mean. On the other hand, if my pet is an insect, we're talking B-movie sci-fi monsters. Now, data can have the same average or mean, but dramatically different variability. If all the scores are clustered around the mean, a small difference is relatively huge. On the other hand, if the scores are all spread out, that same difference is relatively tiny. What is needed to really understand the data and whether a score is small or large is a measure of the variability of the scores. Something that we can use as a yardstick to measure just how big something is. Now, the first thing that comes to mind might be the range of the scores. The range is just the difference between the highest and the lowest score. So if the highest score is 100 and the lowest score is 20, the range is 80. The problem with using the range is that very different distributions can have the same range. Maybe everybody scored 100 and one person scored 20. The range is still 80. Maybe one person scored 100 and one person scored 20 and everybody else scored 60. The range is still 80. So the range is useful but of limited value. Again, you can see that right here. The range doesn't necessarily provide a very good sense of average variability. In fact, the same estimate of range can reflect a lot of variability or almost no variability. Now, it's worth noting that one way of trying to get around this problem is with the interquartile range. The interquartile range ignores the particularly high or low scores and instead is the range that you see between the 25th and 75th percentiles, or the range for the middle half of the scores. Quartiles break a distribution up into 4 equal-sized groups based on the 25th percentile, the median, and the 75th percentile. The value for the 25th percentile is called the first quartile. The median is the second quartile, and the value for the 75th percentile is the third quartile. So again, there are 3 quartiles. That may seem a little odd at first, 3 things being called quart something. But remember, the 3 quartiles divide the distribution into 4 parts. Now, you may sometimes hear people talk about these groups being the quartiles, with people scoring below the 25th percentile in the first quartile and people scoring above the 75th percentile being in the fourth quartile. But again, technically, the quartiles are the specific values that divide the distribution into 4 groups with an equal number in each of the groups. So again, the interquartile range is the range between the 25th and 75th percentile, or just the value for the score at the 75th percentile minus the value of the score at the 25th percentile. If you think back to our video on visually displaying data, you may recognize that the box plot actually highlighted the interquartile range. It's the box in the box plot. But this still doesn't change the fact that the range, whether the full range or the interquartile range, doesn't really tell us anything about how spread out the scores are within that range. Are all the scores close to the mean? Are they all far from the mean or spread out some way around the mean? We need something different, something that tells us how the scores vary around the mean. What about if we sum up the deviations from the mean? These two distributions both have a mean of 10, but clearly there's more variability in the one on the right. So adding up the deviations from the mean may appear to be a good way to measure variability. The problem, as we saw earlier when we discussed the characteristics of the mean, is that the deviations from the mean always sum to 0. Mathematically, that's written as the sum of x minus x bar equals 0. So, if we just use the deviation scores, we have these positive and negative deviations that mathematically always cancel out. We need to get rid of the negative values. One way of doing that is to square those deviation scores. By squaring the deviation scores, the negative values disappear, and we can see that the squared deviations really do capture that variability in the raw scores. If we add these squared deviations, we see that the distribution on the left, where the scores are all clustered together and there's less variability, has a sum of squared deviations only equal to 10, while the distribution on the right, where the scores are spread out, has a sum of squared deviations equal to 362, much, much larger. The sum of squares is very important, and you're going to see it pop up all over the place. Because it's so common, researchers will call it just the sum of squares for short. So write it down, get a tattoo, whatever will help you to remember that conceptually, the sum of squares is a way of describing the total variability that a variable has in our sample. Okay, don't get a tattoo. This specific formula, the sum of x minus x bar quantity squared, is what's known as the definitional or defining formula for the sum of squares. We call it that because it clearly illustrates exactly what's going on. You're taking the deviation of each score from the mean, squaring those deviations, then adding them all up. But if you actually had to go through and calculate the sum of squares by hand this way, this formula is actually pretty cumbersome. You have to calculate the mean, then to calculate the deviation from the mean for every score, then add up those squared deviations. There's a different formula that gives you the exact same answer, but it's easier to use if you're calculating the sum of squares by hand. It's the computational formula for the sum of squares. We call it the computational formula because, well, it's easier to use when you're computing the value. So you may see that formula reported sometimes, but remember, it's just the same sum of squares. It's just easier for you to calculate this way if you're doing it by hand. For us, we're going to stick with the defining formula because I like the fact that it's transparent and clearly shows you exactly what it does. But I have a separate video that goes through the steps of turning the defining formula into the computational formula if you're interested. Now, because the sum of squares is, well, a sum, larger samples will have a larger sum of squares even if the degree of variability is the same. Looking at our illustration with low variability, it's not hard to see that if we had, say, 500 people with the values of 12, 11, 10, 9, and 8 repeating over and over and over again, the mean would stay 10 and the inherent variability would stay the same. But with an n of 500, the sum of squares would now be 1,000. That's a problem because even with little inherent variability, you can have a large sum of squares in a very large sample. While with a small sample, you can have a small sum of squares even when there is more inherent variability just because the sample's small. What we need to do is factor in the sample size. If we divide the sum of squares by the sample size n, we obtain what's called the variance. In that way, it may help to think of the variance as an indicator of the mean sum of squares. Notice that at the moment we're dividing by n because this is our descriptive statistics formula and we're not trying to estimate the variance or anything else in the population. When we divide the sum of squares for our spread out example by n in order to calculate the variance for that group, not surprisingly, we see that the variance is much larger, 72.4. Now, one more step and then we'll be done. Like I said, variance is used a lot in statistics. We're often interested in understanding what influences the variability that we see in scores. Are there things that explain why some kids score high on state tests and other kids score lower on state tests? Are there factors that may explain why some babies are born at a healthy birth weight while other babies are born at a lower birth weight? But if we're interested in that yardstick to measure how big something is, think back to the start of this conversation about rhinos and insects. If we're interested in that yardstick, the variance is a little messy to use because it's based on squared values. Remember, the sum of squares. So let's take the square root of the variance and use that when we're looking for a yardstick to measure something. We call the square root of the variance the standard deviation. If we return to our two small samples, we see that the standard deviation for the group that was tightly clustered together is equal to the square root of 2, or 1.41, with deviations from the mean equal to 0 and plus or minus 1 or plus or minus 2 points. We can see that the standard deviation of 1.41 does give us a sense of the typical deviation we might expect to see. Similarly, we see that the standard deviation for the group on the right that's more spread out is equal to the square root of 72.4 or 8.51, with deviations from the mean equal to 0, 9 points, 10 points, or negative 9 and negative 10 points. We see that a standard deviation of 8.51 similarly gives us a sense of the typical deviation we might expect to see in a group where the scores are more spread out like this. Here we see these three measures of variability. Notice how they're closely related and build from each other. But before we review them one last time, I have to step back for a moment and point something out so that you don't make a common mistake that trips up many students at this point.
Emergency alert. Bad statistics may be in use. Please stay tuned for further information.
Okay, did that get your attention if you were multitasking while watching these videos? If so, great, because I want to save you from making a mistake that students often do in the future. That's These formulas for variance and standard deviation that we're using right now are strictly for descriptive statistics when we're describing our sample. When we get to inferential statistics, we're going to see that we need to slightly tweak the denominator in order to estimate the population variance and the population standard deviation. At that point, we'll change the formula slightly, as well as change our notation in order to estimate those unknown population parameters. Now again, these formulas are correct when describing our sample, but you can't use them later on when we want to infer things about the population. Because of this, there's another thing you need to know, and that's that a lot of software either only reports the variance and standard deviation based on the inferential formula, or they'll default to the inferential version because that's what people typically use. So be aware that if you check your answers using software, you may get a different result if you're using the descriptive formula and your software is using the inferential statistics formula for standard deviation and variance. Okay? Let's return to the formulas. By now, the sum of squares, often abbreviated as SS, should be familiar and should make sense conceptually. It's that total variability around the mean score. Reflecting that the size of the sum of squares will be influenced by the size of the sample. The variance essentially inversely weights the sum of squares by the sample size. Variance is another widely used indicator of the total variability in some variable. Variance based on the descriptive formula with n in the denominator is represented by a capital S squared. Finally, while the variance reflects squared scores, the standard deviation takes the square root of the variance in order to create a yardstick for how spread out we would expect scores to be. The standard deviation based on the descriptive formula with n in the denominator is represented by a capital S. So that's the sum of squares, variance, and the standard deviation, are three key indicators of variability in our data. We use the sum of squares a lot in calculations. And in more advanced work, we'll do all sorts of fun things with variance, using it as a way of understanding variability in scores. Why some children are excellent readers and others struggle, or why some have behavior problems while others don't. We'll also see how we use the standard deviation and variations of the standard deviation as that critical yardstick to measure just how big things are or how large of a difference or effect do we see. We'll start to get into that in our next set of videos when we talk about z-scores. Okay? Bye for now.